Thank you for the introduction. Thanks for the organizers for having me here. So today I'm talking about a very different object that we have not seen yet, which are webs, and you see them on my, at least one of them on my t-shirt. So they look very different from what we have seen this week. But I will convince you there's some connection to non-crossing partitions. That's why it's fitting kind of into this conference. And I should say this is a type A story only. And I'm not the only person having a t-shirt like that. Also my collaborators have t-shirts. So here's Jessica Striker, Oiver Pechenik, Christian Gaetz, and Joshua Swanson. And you may wonder why I'm the only person with the gray t-shirt. This was kind of the prototype. So, and the black one looks a little bit cooler, I guess. Mine is cool, thank you. One thing that's actually also cool, when preparing the talk, I looked at the preprint that we submitted to arXiv, and actually we submitted it precisely 1 year ago on the same date, so February 21st, when it appeared on the arXiv. Okay, so two objects here on the left, we have a non-crossing partition. On the right, we have a web that's actually corresponding to this non-crossing partition. You may wonder, why are we doing such complicated things to something that's that nice and easy? And the reason for that is representation theory. And if you don't like algebra or representation theory, there's only like one slide, and then we jump to more combinatorial things again. What these webs are good for is actually for a problem in invariant theory. Is there a question? So these are webs because Kuperberg called them webs, but web is a too general name, I would say. But yeah, that's right. Some ingredients Kuperberg didn't have, and there are many connections of these objects with other objects, so it's not impossible. Okay, so what's going on with representation theory? So I take my favorite matrix group SLR, and here you can already see why it's different. We don't talk about too much about the Y groups, but we talk about Lie groups here. So SLR group of matrices with determinant 1, and we take V to be the complex R-dimensional vector space, and SLR acts on it simply by taking a vector and the matrix, multiply the matrix with the vector. And we can take a bunch of tensor products. And I take here, for SLR, take R times K many tensor factors and let SLR act diagonally on each tensor position individually. Also note that we have a nice action of the symmetric group on that space by simply permuting tensor positions. All of them. All RK, yeah? The reason why I wrote R times K is because we were interested in the invariant space. And when I would take some arbitrary n here, that would be a trivial space. So what is that space? Invariant, so inf with sub SL and then the vector space in here. This is the space of all the tensors that don't change when I act with any determinant 1 matrix. And we want to study that space. And what I mean by study the space is I want to find a nice basis of that space. It's a linear space, so we want to have a nice basis of it. And with nice, what I mean is a basis in terms of diagrams. And these diagrams, well, these are the webs. Indexed by them, but I would say the pictures are the basis. And a few things to note. So when I would put here an arbitrary n that's not divisible by R, that space is 0-dimensional. And when I have a multiple of R, we get this weird formula for the dimension. Does someone see what that formula is. Maybe in a special case of r equals 2. R equals 2 gives Catalan numbers. K equals 2 also gives Catalan numbers, so it's actually symmetric in R and K. And in general, I would say this is the R-dimensional Catalan numbers. And usually I would tell that story from a perspective of standard Young tableau. So no tableau today in my talk. This is also the number of rectangular standard Young tableau with R rows and K columns. Okay, and if you don't like this tensor product so much, what you can think of this space actually is that you don't take tensor product, but regular Cartesian product of V R times K times, and you want to find multilinear maps where you have like R times K vectors, and you want to map them into the complex numbers such that this is invariant under acting by multiplying with a determinant 1 matrix. Yeah, there's a question. Yes. And if I would not have the R in here, then the space would be 0-dimensional. And then it's 0-dimensional. Then it's a trivial space. Then it's just a 0 vector being an invariant. Okay. I would say it's obvious if you look at crystals, but that's maybe a very different story. Yes, you're actually right. I'm kind of cheating here that I take V and not V dual, but okay. And we already had this question R appearing twice. So what this K here, we give it a name, we call it the Plücker degree. Okay, so this is the setup, this is the space, and maybe to have some kind of example, if I take just R vectors in CR, I could put them into a matrix. Does someone have a cool idea what multilinear map I could find as invariant? Starting out somewhere? Determinant, yeah, okay. So you should think of actually of determinants. A vector space that's probably spanned by something like a determinant. Okay, so we can generalize from this. So if I now take arbitrary Plücker degree, what I can do is, and I'm a little bit sloppy with notation, so I fix some sets, some blocks, some tuple of R indices, I1 up to IR, and then I can take the determinant of just picking R of my vectors. And when I take just any partition of that set 1, 2 up to KR, where I make sure that each block has size R, and I multiply all these, what I would call Plücker variables, I again get a determinant. I again get an invariant. Okay? Yeah. Yeah, I would order them increasingly. So if you rearrange them, you will pick up a sign. But yeah, but so that's why I said I'm a little bit sloppy here. Maybe you want them to be. Yeah, signs are not really important. So okay, so to have an example for SL2 and K equal 2, you can already see I'm drawing partitions here in a little bit weirder way. So instead of making just arcs here, I take a vertex and then connect all the vertices in the block to that one to form some kind of little claw. And so here for SL2, I have 4 vertices and I have these 3 partitions, and these correspond to these 3 products. So 1 and 2 are in a block, so I take delta 1, 2, and 3 and 4 on a block, giving me delta 3, 4. It's it's partitions, not non-crossing partitions. So 1 and 3 are in a block, and 2 and 4, so I get delta 1, 3 and delta 2, 4. Okay. But there are relations between those. So if you write down these polynomials that you get from them, there are these so-called Plücker relations, and they will tell you this plus this is actually this one here. So maybe we shouldn't care too much about here this crossing element, because we have relations like that. And yeah. Now the signs do matter, and that's why I put them in increasing order here. And I can also say that this kind of is actually an identity via these diagrams. This diagram plus this diagram equals this diagram. Okay, let's see if we can make this a little bit more precise on the next slide. So if I take some diagram where I have my blocks and I have some crossing in here, I define some relation between those that I can take my crossing and I can uncross it in either this way or somehow in this way, but I introduce some vertices in between here because I still want to kind of have this bipartite business that I have black vertices and white vertices. So I get this formal linear combination, this crossing equals this plus this. And when I have too many kind of vertices on a strand, I can flatten that out a little bit. I can have some kind of contraction rule here. And if we have this rule in mind and look back here, this one? Okay. If I apply the uncrossing rule here, maybe I directly go there to point. So one way to uncross it is like really this, going up. This gives you this picture here. But if you apply the other way to uncross it, well, then you have here this white vertex. But as the rule is stated, if you replace this top part here, then you get white, black, white, and then we need to contract it away to give this picture. All right, so this identity here is really just applying this rule here. And so it turns out that, yeah? It's kind of applying some kind of contraction twice. What? Or if you have here the crossing, you would get black, white, black, white, black. And then you contract it away and you just get white. Okay. And so it turns out if I start with just any perfect matching, so a partition where all my blocks have size 2. I gave a different rule there. Still? Okay. Okay. We can do it on the board afterwards. Okay. So it turns out that when I have any perfect matching, so a partition to blocks of size 2, I can use these rules over and over and actually write any perfect matching into a linear combination of non-crossing perfect matchings. And so it turns out then the invariants that correspond to these non-crossing perfect matchings are also linearly independent. And so what we get from this, that the invariants that are associated to the non-crossing perfect matchings, where I have 2k boundary vertices, are indeed a basis for the invariant space for SL2. And yeah. Yes. And also note, this is actually a nice basis because I told you about the symmetric group action. I can explain the symmetric group action in the invariant space here by saying how the swapping of two tensor positions is working. So the tensors are kind of the boundary vertices, and what I need to do really to have the simple transposition, I take my boundary vertices, I make them cross, and I apply the uncrossing rules to write it again in a linear combination. And it turns out that the action of the long cycle just is the rotation of the diagram. So if I have my diagram and apply the long cycle, then it just rotated one step. Okay, this for SL2. Well, for SLR, we can try to do something similar, but now the uncrossing rule changes a little bit. So instead of having just these two chains, I have now an edge in between with some multiplicity. The multiplicity here is R minus 2. And you should actually see here some bipartite graph where each internal vertex here has degree R if I add those up. And so it turns out that if I start again with some partition, that I can write where all my block sizes are R, I can write them into a linear combination of what we call an SLR web. And so here's some definition what it is. It's a planar graph, which is bipartite and edge-weighted. It's embedded in a disk such that all my boundary vertices have one color and all my interior vertices have degree R. Okay, many properties, but here you should look actually kind of on my t-shirt. So all my boundary vertices, they don't have the same color. This is even a generalization. Damn it, okay. Maybe we should look at the, should add an example at the slide afterwards. Okay, one thing to note is that we can associate invariants to those webs. So here, if I take kind of my star graph or the kind of the partition where I have just one block, this again is my determinant. So if a single vertex of degree R in the middle, which is wide, and all my boundary vertices have degree 1. Yeah, so I often label them just 1, 2, 3 up to R, but the boundary vertices really correspond to the vectors. Okay, so here's a slightly bigger example. So here you can see this is for SL7, that all my interior vertices have degree 7, all my boundary vertices have degree 1, and it's indeed bipartite where the bipartition is coming from the colors black and white or filled and unfilled. All the interior ones. Oh yeah, and if I don't write a weight, so with degree I mean the sum of the weights, and if I don't write a weight, I mean weight 1. So here 2 plus 4 plus 1 is 7. Okay, and so Curtis, Kamitz, and Morrison are also using some slightly different style of drawing these webs, and Fraser, Lam, and Le, they have actually shown that all these web invariants, they actually span the invariant space, but again, there are some relations. And so there are some relations that look like some contraction relations, and there are some relations that involve squares, and these relations are not so nice to actually work with. And unfortunately, so far, there is no nice basis known for R greater to 4. Yeah? They span all the relations, that's also true, yeah. So with these relations, you actually can get all the relations. But it's hard to extract nice bases out of this. There are various bases out there where people say, yeah, take this map, and the image of the map is the basis, but it's not really a nice basis to work with. And that's where we step in, and you see this diagram looks a little bit different from this one, because here we have these hourglasses. Oh yeah, first SL3 webs. Okay, I forgot that those are in between. SL3 webs are kind of a classical story by Kupperberg from the 90s. So you mostly need this relation here that tells you how to split up a square. And then it turns out that we can write all the SL3 webs as a linear combination of webs that don't have bigons, which I could kind of contract away, or squares. And this Kuperberg calls non-elliptic. And his statement is that the invariants that are associated with the non-elliptic webs with 3K filled boundary vertices give us again a rotation invariant basis of that invariant space. Okay, now to the more general thing. The hourglass plabic graphs. These are just, this is what we define as some kind of new avatar for webs. So here you should see that instead of writing multiplicities on the edges, we put hourglasses in there with some multiplicity m. So we take m strands and we twist them to give some local not planar configuration. And the reason why we do this is because we think of these as so-called plabic graphs that show up in work by Postnikov. And Postnikov uses plabic graphs to define trips on them. And so this is also something that we do. For this, you should think of this as a weird road network where you start at a vertex and you travel along the road, but for some reason, you have some roundabouts which are more like UK style, the white ones, the unfilled ones, and you have some roundabouts which are like US style. So in the UK, you drive on the left side, so you also would need to exit on the left, while in the US, you exit on the right. So here, starting at 9, my trip 1 is I go in, I come to this vertex, I exit on the first step left, I come to this black vertex, I exit on the first right, I come to this white and exit on the first left. And these hourglasses make sure that these trips are actually working. If I would have some bubble, I would go into the bubble, go out, and have some weird loops. But these hourglasses make sure that the trips are properly working. And what I get when I start at any vertex I, come to a vertex j, giving me a permutation. So starting at 1, I would end up at 4. Starting at 2, I would end up at 3, and so on. And this gives me a permutation in one-line notation. Okay, so this is trip 1, but remember here in this example, this is r equals 4. I have internal degree 4, so I have 2 more exits that I can take. Instead of always taking the first exit, I could also always take the second exit. So here, starting at 9 again, I don't take the first exit as before, but I take the second exit of my roundabout and then follow my path. And then here 9 goes to 2. So this is the second trip, and I also have a third trip, which is take always the third exit. Yeah? So here, this is not the first exit, but here's the second. If I would go the reverse, here from 2, I'd then skip the first, but then take the second. So you really look locally, what are my exits, without knowing that you have these hourglasses. You kind of zoom right in, and then you see, oh, I have 4 different exits, and then. Okay, and we use these trips. Actually, they're very powerful in terms of combinatorics, and their antecedents are interesting. Here, to be a little bit lazy, I just say we use those trips to define what it means to be fully reduced. And fully reduced means that your trips avoid some certain bad double crossings. And we also call 2 webs equivalent if they have the same trip permutations. So you have like a trip, and they cross in some point and cross again. Yeah, they cross each other twice. Yeah, special rules that are bad. Okay. Yeah. Okay. And so it turns out for SL2 and SL3, these equivalence classes based on the trips are just coming from contraction relations. And then the contracted fully reduced SL2 webs are precisely the non-crossing perfect matchings that we have seen before. The contracted fully reduced SL3 webs are precisely Kuperbeck's non-elliptic webs. And it turns out for SL4, the equivalence classes are a little bit more complicated, but we can define some kind of top element in there and get that the fully reduced top SL4 webs with 4K field boundary vertices give a rotation invariant web basis. Okay, so that's SL4, and we kind of have a unified way to state all the cases that were previously known. Here, this top kind of indicates already there's some lattice structure behind, and it turns out that fully reducedness can also be characterized a little bit differently. When I look at my trips and I want to understand when do my trips not change, there are some local modifications that I can do in my webs that don't change the trips. So those will give me equivalent webs. And there are two families of moves for SL4 now. There's this benzene move where you have like this chemical element, and we have squares where you change the coloring and then put in some hourglasses or remove them. And it turns out these don't change the trips, but the converse is also true. Two fully reduced webs are equivalent, so have the same trips if and only if they are move equivalent. So if I can find a sequence of moves between my two webs that connect those. And also, webs are fully reduced if in the move equivalence class you don't find some forbidden squares. So remember for SL3, no squares at all, and here squares with hourglasses are forbidden. So in general, it seems like squares where the sum of the weights around it is bigger than R are forbidden. Okay. So fully reduced was a characterization in terms of trips, but now we can characterize it in terms of what faces I see in my webs when I explore the entire equivalence class. A web is move equivalent to itself. So you take a web, you want to know is it fully reduced or not, you explore the entire equivalence class of it by applying all the moves that you can, and then you look, do I find in any of these graphs, do I find one of these forbidden configurations? Yeah. Okay, and these equivalence classes are actually super nice, because if I look at special webs, I actually find some well-known and loved combinatorial objects in there. So if I take something that's looking like just a hexagonal lattice as my web, I will find in my equivalence class a poset, which is coming from plane partition. So here it continues in some direction. And also there's another way to write SL4 webs as what we call symmetrized six vertex style. And then you find in your equivalence classes, coming from the square move, you will find alternating sign matrices, which is also very lovely. Okay, I have not much time, but I still want to talk about Plücker degree 2, because here we again have Catalan number as my dimension. So we do want to construct for the case where I have only two R tensor copies. I also want to find some nice webs, starting with some Catalan object. And the most favorite Catalan object here, it seems to be non-crossing partitions. So here is a non-crossing partition together with its Kreweras complement. So the red thing is the Kreweras complement. And now comes a little bit weird construction. So what we first need to do is we need to group together some of my boundary vertices, and I do that by looking at where my kind of isolated vertices are in this picture. So here 7' and 2 and 3', these are kind of my isolated vertices. And oh yeah, first I made everything gray to don't have distraction from the color, and then I group together in kind of these open, half-open intervals from one of these isolated vertices to kind of just before the next one is. And these one will become white vertices. Then what I need to do is also if I have something that's larger, a block that's larger than a triangle, I need to triangulate it. And then I can, in my triangles, I can make black vertices and connect them out. And I attach black vertices here on the boundary for each of my original boundary vertices. And then these big blocks, I find some weights by some rule. And then I make these chunks here into smaller white vertices like this one here and put hourglasses there. This is not the one that's on the t-shirt. Okay, but this is the one that, that's not even the one that we have seen in the beginning. Okay, this is just some other example to show that construction. Yeah, that's the number of strands in that hourglass. And if they're a larger hourglass, I also like to call them onions because it's getting more and more layers. Okay, and it turns out actually, so we use some triangulation actually of these blocks, but it turns out if I just pick a non-crossing partition, that the associated invariant doesn't change when I choose a different triangulation. If I pick different choices for the triangulation, I still get something that's trip equivalent, so some equivalent webs, and all these webs that I can get are for a fixed non-crossing partition are connected by square moves. And also then using these square moves, it turns out they kind of correspond to flipping diagonals in the triangulation. So before we have seen that the move equivalence classes give me posets for plane partitions, give me the poset for alternating sign matrices. Here I recover the Tamari lattice. And our theorem is that by this construction, I precisely get all the fully reduced SLR webs with Plücker degree 2, so with 2R boundary vertices, and the set of the associated invariants is a rotation invariant basis for the invariant space. And the upshot is that we kind of have now a kind of unified framework for all the known rotation invariant bases out there. And the equivalence classes have nice poset structures where objects that we love in combinatorics also show up. Thank you.